Hello and welcome to this lecture in which I will give an introduction to the nature of battery risks. We will categorize the risks into 4 categories: thermal, electrical, chemical and kinetic. Let's get started. The first is the thermal risk. Lithium-ion batteries have really high energy densities, approximately 90 to 300 watt-hours per kilogram and up to 200 to 700 watt-hours per liter. Now, these high numbers, 300 watt-hours per kilogram and 700 watt-hours per liter, these are not typical values for batteries which we find in mass production at the moment. I think 2 or 3 years ago, the Chinese manufacturer CATL announced that they developed a battery which has even 304 watt-hours per kilogram. But this is obviously development stage and not in the mass market. The temperature will rise when this energy is released without control, for example, during an internal or an external short. But the numbers, the energy densities like 90 to 300 watt-hours per kilogram, this is not the worst case. These numbers apply to normal battery operation, charging and discharging, okay? But in the event of what we call a thermal runaway, and we will have a look at the thermal runaway in a second, during a thermal runaway, battery components can decompose. For example, the metal oxide electrodes and the electrolyte can also be oxidized. These are all exothermic reactions. Okay, and that means that these reactions during such a hazardous event will produce even more heat and heat up the battery even further. The second risk, that is the electrical risk. Battery packs used in electric vehicles operate with very high voltages, which can be as high as 800 volts. There are not that many cars in the market at the moment which operate with 800 volts, but you can find some examples. Obviously, a high voltage will bring the risk of a high current. Voltages below 60 volts are usually considered no risk for human safety, but it can actually be a risk. Just imagine someone accidentally shorting the battery with the wristband of the watch. Wristbands are usually out of metal. They have a pretty low resistance and there will be a pretty high current in the event of a short. And there are people who got burned pretty severely. In all battery labs in which I worked in the past, it was always forbidden to wear any sort of watches or any sort of jewelry. The third risk, that is the chemical risk. Lithium-ion batteries can release flammable and toxic gases. The electrolyte does not necessarily vent as a gas out of the battery. It can also be released as a liquid. The most typical conducting salt for electrolytes, that is lithium hexafluorophosphate, which can form HF, hydrofluoric acid, when in contact with water. And hydrofluoric acid is a pretty nasty acid. And this can be especially critical at high temperatures, when cell components form gases and can leave the cell through some cracks or some vents. The electrolyte is, of course, highly flammable and it's also very, very unhealthy. It is, in most cases, carcinogenic, which means it can cause cancer. The electrolytes are also very corrosive. And of course, imagine a battery system and flammable released gases from one cell or more cells can mix with the air, and you can actually get an explosive mixture. Finally, there is the kinetic risk. A thermal runaway can, under some circumstances, lead to an explosion, and you get the risk of a shock wave and the risk of flying material of high kinetic energy coming from the battery. But this is not only a risk on a single battery cell level. Just imagine the gas-air mixture outside the battery. This can explode within the whole battery module and the whole battery system. As we just saw, battery safety has some dimensions. For one single battery cell, the worst case scenario, that's really the thermal runaway. And the thermal runaway can have different triggers. Triggers which can originate from all parts of the value chain. From producing the active material for batteries to manufacturing battery modules and battery packs. All these processes, when carried out suboptimally, can eventually lead to a thermal runaway. So far we talked a lot about the thermal runaway, and I think I should get a little more into the details. The thermal runaway is a heat-driven process during which the battery keeps heating up. Why does the battery keep heating up? Because the heat produced by the battery is higher than the heat released to the environment. Basically, the battery does not get rid of the heat quickly enough, and therefore the battery is heating up. This is obviously operation out of standard specifications, for example at too high temperatures. So the question which we should ask ourselves now is, what can trigger a too high temperature in the first place? And there are actually different possibilities. There are several failure mechanisms, as we say. For example, external heating, overcharging of the battery, over discharging of the battery, charging at a too high current, the crush, the mechanical deformation of the battery, for example during an accident, the external short of the battery, a structural damage of the battery, and also the contamination of the battery cell during battery production. Sometimes battery cells which are contaminated during production are called ticking time bombs. And there is some cases where car manufacturers or battery manufacturers recalled the end product because they found out about some contamination during battery cell manufacturing. Once we triggered a too high temperature, the solid electrolyte interface begins to fail above 100 degrees Celsius. Now I have to be a little more detailed here. The SEI actually starts to fail at temperatures below 100 degrees Celsius, but you will have a rate of decomposition of the SEI, which is the failure mechanism, but you also have a rate of composition of the SEI. We know that lithiated carbon is not within the stability window of the electrolyte. And at the point when the rate of composition of the SEI is lower than the rate of decomposition, you could say that's the moment when the SEI actually fails. And this is leading to a reduction of the electrolyte, which is an exothermal process. And just for you to remember, an exothermal process is a chemical reaction which will produce more heat. Okay, we have reached a critical temperature. The SEI failed. This led to a reduction of the electrolyte, which is exothermal. The battery cell heated up even more. At one point, the battery reaches 200 degrees Celsius. And that's the temperature at which metal oxides, which are the typical layered cathode materials, start to decompose. We are talking about metal oxides, okay? And the decomposition of a metal oxide releases oxygen. This oxygen oxidizes the electrolyte, which is an exotherm reaction. And we get another rapid temperature rise. The oxidizing electrolyte will heat up the battery even further, and we can reach a few hundred degrees Celsius. The pressure in the battery can increase, the battery cell can burst, and there is the risk of a fire and even an explosion. So let me repeat. The thermal runaway is basically a stepwise process where the different steps in this scenario trigger the next step. Basically, one chemical reaction can happen at a certain temperature. Once it happens, it releases heat. This gives the battery the possibility to get to an even higher temperature. This even higher temperature can trigger the next step of the process, and so on. So, can we stop a thermal runaway? Technically, yes. If we can somehow get rid of all the heat which is produced and we do not reach the next step of the scenario. But in most practical setups, it's not really possible to stop the thermal runaway. And that's why the strategy to avoid a thermal runaway is mostly to avoid the first step of this process, to avoid the first trigger.